Let me start the remaining part. Okay, what is the theorem? Sorry. Let F be a field and Px belongs to Fa. It's irreducible polynomial if then extension field of F that has a root alpha of Px then F alpha that will be isomorphic to X. That is my claim here. So here K is an extension field, okay, that contains alpha. So the fact is that I could not get alpha, or I might get alpha. I don't care. If I don't get alpha, I stretched to a field extension which has alpha. Then if adjoint alpha, so that is the field containing alpha. Okay. Okay. So then they are isomorphic. That is the theorem, okay? Because that might be an ugly looking field, but that is simply, you can tell the elements of it. Proof. Let us I fx to f alpha by phi of fx equal to alpha. It is actually evaluation. That the it is evaluation at the bottom. Then one can verify phi is homomorphism. Yes, obviously. Now Px belongs to kernel of psi because P alpha is 0. So by the universal property of quotient ring, we have a map psi. It is the universal property. Okay. What the universal property says? if R2S is a ring homomorphism, phi, and I is a map, so I is a map, is an inclusion map. Okay. So R2S is the homomorphism and I is an ideal such that I is contained in kernel of phi with the homomorphism phi. Then there is a map from R mod I to S such that the diagram is commutative. Okay. But if X mod Px is a field because as Px is irreducible. So it is a phi. So what is phi? So sorry, psi is a field homomorphism which is injective. So psi is injective. Okay, because it is non-zero map. Okay, it maps 1 to 1, so it is a non-zero. So if a field ring homomorphism is field homomorphism is non-zero, it must be injective. I proved this. Okay. Now observe one thing. So by first isomorphism theorem, of rings, we have sorry. This thing that is contained inside F alpha. Now, see, this image is a subfield. Okay, it is a field. So the image, homomorphic image, that will be subfield, and that contains F because this left-hand side contains F and also contains alpha. Okay, because I assumed that. What I assumed, K contains alpha. So this contains alpha. I mean the isomorphic copy of alpha. What will be the isomorphic psi of alpha? That will represent alpha. Now, F and alpha, and it is a field, and it is a field. So it must contain F of alpha. What is the reason? Because it is the smallest subfield. And it is any subfield, any field containing F and alpha. as f of alpha is content inside also this thing, which is isomorphic to this, which is again content inside f alpha. So if you think the isomorphic things as same thing, it is equal because algebraically the properties are equal. Don't need this. From there we can say then they will be equal. I need isomorphism. So if you compose the map, then you will get the isomorphism. Which shows that f x y. What we did, simple thing, just took the map. So it is a subfield. It is a field homomorphism, so injective. Now if alpha is the smallest subfield, you use that. We are given that K contains alpha, okay? Otherwise, it is the inclusion would not be possible. That will be not possible. Let's see. Fine, I think. What is F alpha? Again, F alpha is this thing. So, as a corollary, corollary, same notation. If degree of Ex is n, is F alpha. F alpha will be alpha 0 plus alpha 1 alpha. Okay? Because see, the importance of this thing is that alpha 0, so F alpha is quotient of two things. in the above there is alpha polynomial in alpha, in below there is polynomial in alpha. So this result says that only that numerator thing will be polynomial in alpha. Below thing need not be. Below thing will not. That is a different. See, f alpha is not like this. F alpha is obviously of the form, in the numerator there are some polynomial and denominator there is polynomial. But this theory corollary says that using this result we can say that f alpha is of the form of this thing. What is this? This is actually f alpha to degree n polynomial. Understand why this is true? Because let me see whether we did, in the previous class. It was on the previous class. Yes. One minute. Yes. This is what this thing. See, f theta g theta is equal to arc theta. So the polynomials up to degree n, there will be only. So if, I mean, what is this? Px was degree n polynomial. Now, if so, fg is less than n degree polynomial. Okay. So that was the main thing of this theorem. And also we used that thing. F alpha is isomorphic to k. I mean, f alpha is isomorphic to f x modulo px. Now we know that multiplication formula in that previous lecture I showed you. Now using this you can conclude this. Just take a time and think. So few examples. What is, so from the example we can directly say that qx mod x square minus 2 is isomorphic to q. Sorry. It is isomorphic to q root. So actually what we are doing in the previous case, in past talks, we are denoting root by x bar. Same thing. We are attaching roots actually. So what is the importance of the lemma? The importance of the lemma is, if you take that thing is nothing but attach a root. The thing is this. So one can also think but they're isomorphic. But they're same actually, not isomorphic. Even. Q root 2 over Q is generated by, it was generated by 1 comma x bar. Now x bar is generated by root, replaced by root. Second example. Think of this thing. Okay. Again, by the same thing, we get this. Then it is exactly equal to, by the corollary, alpha root. So this is the root we attached here. So it will be of the form uh, okay. Now this is the example. But it is over Q. But if we consider the thing in R, then we will get some complex roots also. I mean, that equation also have solutions in C, but we are confined ourselves inside Q. So other solutions will not be there. I think it is clear to you. Just have a look. I mean, we are interested to see the solutions in R here. Sorry. I think it is wrong statement. That is the basis over Q. Okay. I will come back to this. That is not correct because you brought up unity is there. Actually, this is in some other field. We can do this. that will be A plus B. That is correct thing. But the isomorphism need to be checked here. Belongs to Q. It is exactly equal to, sorry, for the confusion, it is isomorphic to this thing. Obviously. Yeah. Okay, it will be, no problem. It will be. Because of that same formula. So I am going to the next theorem. So it is better to say that that is an observation. Again, I will make an observation. Let isomorphism of fields. Okay. So we can get a ring isomorphism psi, which is from f dash x, which is from f to f x to f dash x, such that I mean not such that I bring phi to the coefficients. I can get this. I mean that means psi of fx will be, I mean if fx is suppose ax plus b, then psi of fx will be phi a x plus phi b. That means phi of x plus b. That means phi of fx. Okay. So now if px is an irreducible polynomial, that image will be also irreducible polynomial. If px belongs to x is irreducible. image in f dash x, say irreducible. What is the reason? If px equal to p1x, p2x, then psi of psi of px equal to psi p1x, psi x. But psi is an isomorphism, okay? So it maps non-zero entity to non-zero entity. So it never decreases, it will never decrease the degree. So it will preserve the reducibility here. So if this is properly decomposable, that will be again properly decomposable. That is the correct. That is the result. Now the irreducible means maximal ideal. Irreducible means maximal ideal. So Ix map the maximal ideal Px of fx to maximal ideal f dash, sorry, f dash x. Actually, this psi of px will be denoted by p dash x, right? Psi of p dash x. From this, we can conclude the important theorem. Which is will be important in the splitting field sense. So I am saying what is the statement of the theorem says. Okay, then I will. So suppose you are given a isomorphism. Okay, you denote it by phi. Isomorphism between fields. Now here you get an irreducible polynomial. Here after applying psi, which is induced from phi, you will get another irreducible polynomial here. Okay. So in fx level, so I should write here more punctually. This f is inside fx, is f dash x. So they are considered inside this. So fx inside fx there is px, sorry, there is px, there is p dash x. So I can get psi here. So if alpha is a root of px in fx and beta is a root of f dash x in p dash x, of p dash x in f dash x, then f is isomorphic to f dash beta. Okay. Actually, if I what does it mean? If I apply this and get another field f dash beta, okay, then they are two are isomorphic. Where alpha and beta are the roots of px and the roots of the root of p dash x, where p and p dash are we get by this thing. Okay, it is very easy thing to prove. Delete. Let me write down formally. Let fields let x belongs to x be irreducible and p dash x belongs to f dash x be the polynomial obtained by applying psi to the coefficients of px. Okay, let alpha of px in some extension that might not be in f. Okay, that might in might be in some field extension. That p dash x in some extension f dash. F alpha is isomorphic to f dash. So, because what is the thing here? What is the main theme? The main theme is that we are starting with an isomorphism. We are getting back another isomorphism. Okay. I am again explaining the statement. I am again explaining the statement. So suppose you are given a field isomorphism. Isomorphism, I am saying isomorphism. Now, in fx, you can consider px. In f dash x, you are considering this thing, which is we get by applying phi. Then, so that polynomial has a root on some extension. Let the extension be k. So you can attach the root, get f alpha. The smallest, I don't need here k fully. That extension gives you similarly f dash beta. Then the two things are isomorphic. Sorry. So start with an isomorphism this, you will get this. The proof is very easy. So as in the previous observation the isomorphism phi, phi would induce a ring isomorphism fx between x and f dash x, such that the maximal ideal px be mapped to the maximal ideal p dash x. X of fx. That we know, that is by the previous isomorphism. So there is another isomorphism. So as a field, they are isomorphic. Because it is, I think it is given by the simple map, that is fx plus fx goes to, I mean, phi of fx plus p dash x. That is the isomorphism. You can, or other, also you can prove by explicitly defining and proving the kernel is this. I mean, let me give some hint. That also denote this by what is size used here, no? No. Sorry. It's two. Plus. Plus. So what is the kernel? First of all, observe that this is fx, this is a, I mean, onto map. Observe because this projection map compose the isomorphism. That what you name the isomorphism, I don't know. Compose isomorphism. Okay. Let me write it as pi compose. If one where one is I mean that isomorphism. Sorry, that isomorphism. Name the isomorphism F1. So obviously, first I apply fx to f dash x by this map, then apply the projection map. So this map is isomorphisms onto map, and pi is onto map. So composition of two onto map is onto. Now what is the kernel? I need to find out. Kernel of psi. So all those fx belongs to fx such that phi of fx plus p test of x equal to p test of x. That means all those fx belongs to fx such that phi of fx contained inside now observe that px is inside kernel. Which implies that ideal generated by px will be inside kernel of C. Oh, sorry. That is fine. Also, px is maximal ideal. Why it is maximal ideal? Because it is irreducible. Because it is irreducible and kernel of psi is not equal to fx. Why? Because if we look the map 1, I look the image of 1, then it is not 0. Then it will go to some 1. It will not go to 0, I mean. 1 will be not mapped into some class of p dash x. It will map to 1. 1 equivalence class of 1, which is not p dash x. Okay. So this map, this is must be equal. Otherwise, there will be the full ring, but 1 is not there. So actually, px equal to kernel. Thus, by first, you understand why I wrote this? The logic is this. Logic is this. Okay, so again there is an observation. If I mean, okay, let's not go further. Although one thing can be told that okay, let's not go just further. I will conclude the class here. Thank you.